So this is a JK flip-flop. So we saw the truth table of a JK flip-flop previously. So we know that in a JK flip-flop, if J equal to 1 and K equal to 1, then uh, Qn plus 1 equal to Qn bar. Okay, this is what we know. So using this, we'll just analyze this particular circuit. So suppose the previous state of that is Qn. Qn is say 0. So Qn bar will be 1. That is the previous state. Now I am applying J equal to 1 and K equal to 1. So I need to know what is my Qn plus 1. So J equal to 1, K equal to 1, I am applying the clock. So I'll take the previous state here. So this will be 1 and here it will be 0. So since this is 0, this is 1. Since all these are 1s, this is 0. Since this is 0, this will go to 1. And since this is 1, 1 will come here and this will change to 0. So that's why you call that Qn plus 1 equal to Qn bar. Okay. Now the issue here is with the clock. Okay. So suppose this is my clock. Okay. This is my clock. And suppose this is you get this output when the clock is high. Okay. So at this particular time, the clock is high, and at that time I got from 0 the output changed to 1. Now suppose this, when this 0 to 1 change happened, okay, 0 to 1 change happened when I applied the clock, this particular clock. Now after this change happened, that is now Qn plus 1 is 1 and Qn plus 1 bar is 0, still my clock is still high. Okay, so what I mean is I'm just going to expand and draw this particular clock. That is, my clock is suppose this. Okay, and at this particular point I applied the clock. Okay, my clock becomes high here at say time t1, and at say time t2, suppose I got this one, that is 0 changed to 1. Now still my clock is still high. This is not the next clock, this is the same clock. Okay, because this is one clock. Okay, the next clock means the next time it becomes high. Okay, so when it reached t2, at time t2, my output has changed, but the problem is that the clock is still high. So what happens is, there is a feedback from the output to the input in the case of a JK flip-flop. So when this changes to 1, that 1 automatically comes here. This 0 comes here. So what happens? This will change to 1 and this will change to 0. When this changes to 0, what happens? This will change to 1. That 1 will come up here and this becomes 0. So what happened? I applied only one clock. Okay. In that single clock, I got two answers. I just applied a j equal to 1, k equal to 1. That's it. My previous state was 0. So I should get the next state as 1. That's it. Okay. It should not change any further. But since that change happened, qn bar, qn plus 1 equal to qn bar, that change happened at t2 and still my clock is high. And since there is a feedback from the output to the input, what happens? The clock is still high. This is still 1. So my output will again change. Now suppose this particular change happened at say time t3. Again my clock is still high. So what happens? This 0 will come here. This 1 will come here. So this will become 0. This will become 1. This becomes 0. This becomes 1. And that 1 comes here and this becomes 0. So for a single clock, I got so many outputs. When my previous state was 0, I gave j equal to 1, k equal to 1 and applied the clock. I should get only this 1 and this 0 here. Instead, for the same clock, I applied the clock only once. I did not reach here. This is my second clock. This is my first clock. This is my second clock. In the first clock itself, I got many answers. So that is an issue with the JK flip-flop. That is when j equal to 1, k equal to 1. Since my output qn plus 1, that is the next state is qn bar, the output will toggle for the same clock pulse. For one single clock pulse, the output will start to toggle because it is qn bar. If it was 0, 0, it is qn, so it will remain the same. If it is 0, 1, the output is 0, it will remain the same even if the clock is applied for a long time. If it is 1, 0, the output will be 1, it will remain at 1 itself. But since in j equal to 1, k equal to 1, qn plus 1 equal to qn bar, it is complementing. So the output will toggle, that is output will go from 0 to 1 to 0 to 1 to 0 depending on the width of the clock. So that is an issue with the JK flip-flop, and this issue is called as race around condition. Okay, this issue is called as race around condition. So that's an important question which you will be asked. What is race around condition? And explain the race around condition. Now, how do you eliminate this race around condition? So the main issue here is that when I apply a j equal to 1, k equal to 1, after the output, after we get the correct output, the clock is not changing. Okay, so you can say that the clock should change after I get the output. So make the clock smaller. That is, if my clock was like this, high only for a certain amount of time, after that, after I get the correct output, it is going low, so that this issue won't happen. But then that's not possible, because already the clock is quite low. Okay, so you cannot reduce it further, because in some cases, in some circuits, you won't get the correct output if you reduce the clock width any further. So reducing the clock width is not possible. Now another method is the output. You will get the output, or the flip-flop is triggered only at an edge of the clock. That is, this is a positive edge, that is 0 to 1 transition. This edge is called as the positive edge, and 1 to 0 is called the negative edge. So you can make the flip-flop a positive edge triggered flip-flop, or a negative edge triggered flip-flop. That is, the flip-flop will work like we say that clock equal to 1 means you will get the output. Just like that, the output will be obtained only during the positive edge or during the negative edge, any one. Positive edge means when it goes from 0 to 1. So that's a very small time, because this is a pulse. Instantaneously it will go from 0 to 1. Okay, so the flip-flops which are triggered during the positive edge of the clock pulse are called positive edge triggered flip-flop, and the flip-flops which are triggered during the negative edge of the clock pulse is called the negative edge triggered flip-flop. So if this is a flip-flop, say JK flip-flop, if you put like this is a positive edge triggered flip-flop. And in a flip-flop, if you put like this, then that's a negative edge triggered flip-flop. You have a bubble here, then the arrow. Here you just have the arrow, no bubble. Okay, so you have both in practical, in normal means you have positive edge triggered flip-flops and negative edge triggered flip-flops, but normally in labs we will be using negative edge triggered flip-flops. So that is one method. Now the most popular method which we use to remove the race around condition is using a method called the master slave flip-flop. Now what is that? So for a JK flip-flop you need 4 NAND gates. So in a master slave flip-flop you have another 4 NAND gates. And this goes to the last stage, just like in the case of JK. So if you see here we can see that This is a JK flip-flop. This is another JK flip-flop. In the first section, you have two sections. In the first section, this is controlled by a clock. And in the second section, it is controlled by clock bar. This is clock bar. So, when clock is equal to 1, the first half will work. When clock is equal to 1 here, it will be 0 here. So, this part will not work. When clock is equal to 0 here, this part will not work. But here it will be 1. So, the second part will work. Okay. So, we'll again see if it is 0, 1, the earlier case. J equal to 1, K equal to 1. J equal to 1, K equal to 1. And clock is equal to 1. So, here it is 1, here it is 0. So, here you have 1, 0. There 0 means here it's 1. And here it is, since this is 1, this is 0. Now, here you have a 0. So, these 1 and 0 will not pass to the second stage. It will remain here because this part is not working. Because clock is 0. Okay. Now, after some time, we have not changed the inputs, nothing. After some time, the clock will go to 0 because clock means clock is 1, clock is 0. So, after some time, the clock will go to 0. So, when the clock is 1, you got the output of the first stage and that is applied to the second stage as the input. But second stage output, which is our actual output, this is our final output. This we have not yet got. This is my Qn. Qn bar, not Qn plus 1. So, in order to get the Qn plus 1, we should wait for some time until the clock goes to 0. So, when clock goes to 0 here it will go to 1. Yes. So, this becomes 1 when clock goes to 0. So, this 1 is applied here, this 0 is applied here. It comes 1, this is 0, this is 0 means this becomes 1, that 1 comes here and you get a 0 here. So, you got Qn bar itself, but and this is applied to the first stage. This is applied to the first stage. That was my problem with the JK flip-flop because there is a feedback to the first stage. There is a feedback to the first two NAND gates. There will be a change in the output. But this second transition happened when clock is equal to 0. So, you are getting Qn plus 1 and Qn plus 1 bar when clock is equal to 0 here. So, here clock is equal to 0. My inputs have changed, but there is no issue because clock is 0. So, the output will not, the first stage output will not depend on the inputs. Okay. So, even if there is a change here, this will not change because clock is 0. Because the first stage is not working. Okay. Now, after some time, the clock will go high. So, that is the next clock. So, my issue was, that is the race around condition is for the same clock pulse. For a single clock pulse, I am getting multiple outputs. So, this is the next clock. In the next clock, I can change my inputs. Okay. So, for the next clock, if the output changes, that is not an issue. That is not race around condition. So, in this particular circuit, The first stage output is obtained when clock is equal to 1. At that time, the final output is not changed. We are looking only at the final output. My LED is only here, Qn plus 1. Okay, so here there is no change. When clock becomes 0, here there is a change. That is fed back, but at that time clock is equal to 0. So since this does not change, this is remaining the same as before, my final output does not change for that entire clock pulse. So that thereby we are removing the race around condition, and this is called as master slave flip-flop. Now the first section, this is called the master, and the second section is called the slave, because here you are getting 1 0, here also you are getting that 1 0 only. What was the output at the first stage? The same output you are getting at the second stage. So this is a slave which will follow the master when the clock is equal to 0. When clock is equal to 1, master will give the output. Same output the slave will give when the clock is equal to 0. So slave is following the master in giving the output. That's why you call it a master slave flip-flop. And most of the flip-flops we get in day-to-day life is a master slave flip-flop. So you don't have the race round condition as such. Okay.